Good afternoon, everybody. You just said my name is Bryn Davies. I'm from the Department of Mathematics at ETH Zurich, and it's really a pleasure to be here. Of course, today here is my living room in Zurich rather than Vienna, but nevertheless, it is a pleasure. I'd like to thank the organisers for making this event happen. I'm delighted that it's going ahead in online version, and grateful for the opportunity to come and share this work with you. So the work in question concerns analysis of sub-wavelength resonance problems. It represents a series of collaborations both with Habib Mari and also Eric Hiltunen, who are both here at ETH, but also Hyundai Lee, who's over in Inha, and Sang-Tin Yu, who used to be at ETH but is now at Korea University. I should say before I start that our group, Habib Mari's group, doesn't do that much in the way of imaging these days. That's reflected in what I'm going to talk about for the next half an hour or so. But nonetheless, I hope that this analysis and the associated applications will be of interest to you. So before I go into specifics, allow me to start by giving some context. So we're interested in studying the occurrence of resonance in structures whose dimensions are much smaller than the operating wavelength. This is a remarkable and powerful and at times somewhat counterintuitive phenomenon, which requires the use of sophisticated mathematical techniques in order to understand it fully. And in the setting of acoustics, really the classical example of this was observed in the early 20th century by Marcel Minnaert during the course of his study of the acoustic properties of air bubbles in water. And in particular, he observed that by judging the pitch of the sound that a bubble makes, which he judged by ear, he was able to derive formulas which related the resonant noise that a bubble makes with its size, which he measured using this apparatus at the top here, and was able to demonstrate that a bubble resonates with a wavelength that's somewhat greater than its size. And this is not only an interesting phenomenon, but this property, that air bubbles act as very strong scatterers, even at very small scales, means that they can be used as the building blocks for much larger structures. For example, this is the experimental setup from a team at the University of Manitoba who were able to reproduce this behavior using gas bubbles injected into a polymer gel, which firstly replicates the material parameters of air and water quite well, but also has a relatively high viscosity, meaning we can start to design complex structures with a variety of exotic properties and applications. And when we're doing this, these complex microstructure materials are really examples of metamaterials. Metamaterials being this very active area of research during the last couple of decades. A brief history of which is that it more or less began with the development of materials with effectively negative refractive indices, from which researchers were able to develop high-profile devices such as perfect lenses and cloaking and shielding devices. But in the roughly 2 decades since then, this field has grown rapidly, and in particular, acoustic metamaterials have come to the point now that they're quite close to commercial application. For example, last year Nissan shared details of this honeycomb lattice structure, which acts as a very effective yet lightweight broadband sand insulator that can be specifically designed to reduce road noise in cars. So that's kind of the background. To be more specific, I'll speak in 3 parts, or start by presenting some analytic results, which we'll use to describe the sub-wavelength resonance problem. Once we've developed this theory, I'll then move on to looking at 2 examples of it in action. The first concerns designing biomimetic metamaterials based on the cochlea, and the second is an analysis of active metamaterials, which can be designed to have higher order resonances, in a sense that I'll make precise shortly, such that they then have applications in enhanced sensing problems. So let's get started. So we're interested in studying acoustic scattering by a collection of disjoint material inclusions, which I will refer to as the resonators. And we want to characterize the resonance of this system in the case that the incident wavelength is much larger than the structure. And we're going to study a Helmholtz formulation like so. Now, in order to capture the subwavelength behavior of this system, there are a variety of traditional approaches that we could use. For example, we could consider performing asymptotics in terms of either the low frequency limit or the limit of small particle size. In the field of studying these complex microstructured metamaterials, homogenization techniques are also very commonly applied and work very well. However, in this work, we're going to take a slightly different approach and instead consider the asymptotic limit in terms of the material contrast parameters, which are these deltas that appear in the continuity of flux on the boundary. We'll consider the limit as these get very small. And the advantage of this approach is that the limiting problem when delta is 0 is non-trivial, in the sense that it has non-trivial resonant solutions, which I'll define precisely in a moment. Because the limiting problem has this kind of non-triviality to it, we're then able to study the system for small non-zero parameters as a continuous perturbation of that state, thereby both deriving asymptotic formulas and also proving existence results, as we will see shortly. Indeed, we will define the notion of subwavelength resonance as an asymptotic condition, which says that subwavelength resonance is subwavelength if the frequency converges to 0 as a function of delta. And as we'll see, this approach will kind of reveal some of the mechanisms that makes this phenomenon of subwavelength resonance actually fundamentally different from typical wavelength type resonance. And in addition, we're able to use this approach to understand the near field behavior of a system of resonators with fixed position and size, which is not the case if you start to do asymptotics in terms of the position or size of the resonators. Okay, and as we'll see, the results of our analysis has at their heart the notion of capacitance. And for a system of material inclusions in 3 dimensions, we can define the capacitance coefficients like so. That is a set of integrals involving the Laplace single layer potential. These quantities have been studied extensively, particularly in the setting of electrostatics, wherein they were first introduced by Maxwell, and they're used to relate the distributions of potential and charge in a system of conductors. In our setting, when we're studying Helmholtz, the fundamental idea is that, of course, Laplace is the low frequency limit of Helmholtz, and it will turn out that actually the object that we were interested in is the following, which we refer to as the generalized capacitance matrix. Generalized in the sense that it's the capacitance coefficients, but with this weighting term in front. And this weighting is able to account for potentially different sizes of the resonators, as well as possibly different material parameters. And the main results of this analysis will look like so, or at least the ones that I want to highlight today. So if we define a subwavelength resonant frequency to satisfy this asymptotic condition as a function of delta, then we have firstly that a system of n subwavelength resonators has n subwavelength resonant frequencies with positive real parts. And additionally, we can go a step further and say that these resonant frequencies are given at leading order by the eigenvalues of this generalized capacitance matrix defined on the previous slide. So I'd like to spend a couple of minutes giving some insight into kind of how we arrive at this result, because I think it really demonstrates kind of the key points of this analysis. The first step is, we're doing boundary integral equations here, so the first step is to realize that we can represent solutions to this Helmholtz problem using the corresponding Helmholtz single layer potential. And the value of this Green's function approach is that it reduces this three-dimensional wave scattering problem to one posed on the boundary of the resonator's D, and it means that we're left only having to find densities phi and psi, defined, which satisfy the two transmission conditions on the boundary. And when we do that, we arrive at a boundary integral equation like so, which involves this Neumann-Poincare operator K. And now we see kind of the value of this theory is that now our investigation of this subwavelength resonance comes down to understanding the kernel of this operator A, this boundary integral operator A, for certain omega and delta. In particular, given this definition of subwavelength resonance that we made a moment ago, which is small delta implies small omega, we're interested in studying the kernel of this operator A in the case of small omega and delta. And with that in mind, we can start by studying the limiting case, for which we have the following lemma, which says that we have these A0 involves these two operators. It says firstly that the single layer potential is invertible in 3D, the Laplace single layer potential, that is. And secondly, that the eigenspace of the Neumann-Poincare operator corresponding to eigenvalue 1/2 has a basis like so, given by these functions, which you'll recognize as being the integrands in the definition of the capacitance coefficients, which is exactly where that comes from. And so with this in hand, we can then move on to studying the problem for non-zero frequency and material contrast delta. And the argument is something like the following. So we're using this information about the kernel of A when omega and delta are 0 to argue for the existence of corresponding low frequency modes when omega and delta are sufficiently small. In particular, we're showing that for omega and delta in some neighborhood, 0, there exist the same number of resonant modes as for the trivial case, as for A0, counted up to multiplicity. And we can also, because we have asymptotic expansions for the B and C on the slide here, we can also compute asymptotic expansions for the solutions, and that's how we arrive at the result. And so this analysis gives us both existence and also expansions for the resonant frequencies in terms of the eigenvalues of this capacitance matrix, which is nice, but it also tells us an extra thing, which is that the corresponding eigenmodes are given by the corresponding eigenvectors of this generalized capacitance matrix. And now these two results taken together, which ultimately just describes the behavior of an n-body system in terms of an n by n matrix, are, at least in that respect, nothing particularly eye-catching. However, the reason that I quite like these results is that it kind of strikes a nice balance. So on the one hand, these are rigorous results derived from first principles and have explicit error terms, which we can study and we can work with when we want to. But also it's very concise. So ultimately, we've ended up with an n by n matrix which we can readily use to handle a variety of important applications, as we'll see in just a few seconds. Just briefly before we move on to doing some applications, we can also apply a similar analysis in 2 dimensions. Here, the picture is slightly complicated by the fact that the Helmholtz-Green's function has a logarithmic singularity at 0 frequency. And on top of this, the Laplace single layer potential is, of course, not generally invertible in 2 dimensions. And so instead, we have to use this sort of modified version S hat, which is invertible. But nevertheless, we can follow similar steps to arrive at a result which gives the characterization of the behavior, albeit less concisely than in 3 dimensions. Okay, so now that we've got some theory ready to use, let's turn our attention to doing some applications. So the first of which is the design of cochlea-like metamaterials. So briefly some background. So the cochlea is this small spiral-shaped organ located deep inside the head that's really at the center of human hearing. It's here that sounds are filtered according to frequency before being converted into neural impulses, which are then sent to the brain. And there have been numerous attempts to design biomimetic devices that mimic cochlear function. These have applications both in designing and building artificial hearing approaches, but also conversely for helping to reveal insight into the fundamental mechanisms that underpin human hearing, the biological system. This is a really common motivation for some of the researchers that worked on this, and I'll discuss this more in a moment. And these devices have been quite wide-ranging in nature, but are all generally based on some graded array of resonators in order to replicate the frequency separation that the cochlea performs. And using our analytic approach based on this generalized capacitance matrix, we can likewise study a graded array of resonators and begin to understand the extent to which it mimics the cochlea. And so, for example, if we look at the left-hand plot here, we can see that we can set up the structure such that it can be designed to mimic the relationship between frequency and position of maximum excitation that exists in the cochlea. Likewise, on the right, the transmission properties of the array, this is a progression over time, also match what's happening in the ear, whereby this peak amplitude travels slowly through the array up until the resonant place. Now, probably the biggest, so these results are nice and a useful starting point. However, probably the biggest open question in auditory science concerns the precise details of the amplification mechanism that's used in the cochlea. So the cochlea is not just a passive sensing array, but has active elements which we can mimic by adding forcing terms to the differential problem. And with our framework, we can start to investigate the effects of different nonlinear forcing terms. For example, if we take this Hoff-type nonlinearity, which is a popular suggestion, shall we say, then we can do things like begin to investigate stability, as demonstrated by the phase space plot on the right here, and also investigate the induced amplification effect. So it's shown on the left here for 3 different volumes of sound. And from this, you start to see the kind of fundamental reason why this non-linear amplification is so important, is it means that quieter sounds, which is represented by the solid line here, are amplified much more greatly than louder ones. And it's this mechanism that allows humans to hear sounds ranging over such a wide range of volumes. And so from these primarily numerical investigations, we can see the real value in developing and studying these cochlea-like structures. That is, that this non-linear modal analysis that we're doing here in our artificial setting is pretty reasonable. It's perfectly doable and allows us to draw conclusions. However, the corresponding analysis in the biological setting is more difficult to the point of being almost unfeasible, because the cochlea is this full of very complex structures and is more or less inaccessible to direct experimentation, at least on living organisms. If we return to the passive case, we also have the following lemma, which describes the scattered field in terms of the resonant modes, which are the UNs, which we described a couple of moments ago. And so what we have here is a physical structure that is designed to filter sounds in a way that replicates how the human ear does it, as we've discussed. And now, of course, one thing that one can realize is that there's a very large signal processing community trying to design algorithms that more or less do exactly the same thing. And so our emphasis of our kind of recent investigations has been based on the realization that with results like this one in hand, we can use this as the starting point for building biomimetic signal processing algorithms. And so if we take, using the frequency domain coefficients that look something like the top here from the previous lemma, then we see that this scattered field behaves something like a series of convolutions with these kernel functions hn. And these hns are, it turns out, first order gamma-tones. And this is nice for a few reasons. One of the most eye-catching is that a variety of other biophysical or numerical studies, some examples are listed here, have also concluded that these gamma-tone kernels are the right choice if one wants to mimic the function of the human auditory system. So that's nice, and then we've kind of gone a step further with this principle of biomimicry at the front of our minds and trying to mimic how the biological system does it. We've also built on this further by trying to mimic the ability of humans to identify long-range global properties and structures in a sound. So in particular, as an example, humans are known to be well adapted to hearing a class of sounds known as natural sounds. These natural sounds, which are a whole class of human and animal vocalizations, environmental sounds, these sorts of things. These sounds have been observed to have certain statistical properties. And thus, if we take a signal, which has been filtered by our cochlea-like array, which we've designed, then we can expect that the output will be governed by these certain statistical distributions, from which we can extract a small number of parameters which describe the global properties of sound, and does it in a way that mimics how humans do. And so some examples of these distributions are shown in these plots, and this is kind of a source of ongoing investigation. So the final example that I'd like to discuss concerns the use of, or the study of active metamaterials and their use in the design of so-called enhanced sensors. So what do we want these enhanced sensors to do? So we want them to be able to sense small local perturbations. So for instance, perturbations caused by the introduction of a small particle, as sketched here. And typically, such an occurrence would cause a shift in the resonant frequencies that is, roughly speaking, proportional to the strength of the perturbation. So in this case, proportional to the size of the particle. The idea here, however, is to design an array for which this shift is enhanced, greatly enhanced, particularly for small perturbations. And the idea to do this is to add sources of energy gain and loss, so damping and amplification, and then fine-tune the parameters accordingly. We'll go through the details in a moment, but devices based on these principles have been designed and implemented. For example, here's a really nice example that was in the setting of photonics. So we've got a 3 resonator system that has gain and loss implemented through heating elements. And then on the right, you can see the desired enhanced response, whereby particularly for small perturbation strengths, the frequency splitting, as they call it, is well above linear. Now, the result that's really at the heart of what we're trying to do here is the following. And this says that if a lot of text here, but this says that if a system's green function has this nth order singularity, and then you introduce some small particle, which we're calling capital omega, then one of the eigenfrequencies will be perturbed with a perturbation that scales in the order of the volume of omega, the power of 1 over n, where n was the order of this singularity. And thus, our aim is to design systems that have such higher order singularities. And one way of doing this, one reason for these singularities to occur is at an exceptional point. An exceptional point being a set of parameters at which eigenvalues and eigenvectors of the system simultaneously coincide. And these exceptional points are essentially a consequence of balanced symmetry in the system. And hence, people commonly search for them in structures with parity time symmetry, just as an example. And so some examples of this, the photonic example from a few slides ago is symmetric in the sense that it's a symmetric geometry, but you have gain and loss enforced in a matched way on either side. People have also studied sort of symmetric Hamiltonians of this form, and on more relevant to the kind of things we're trying to do, people have also found ways to implement loss and gain elements in acoustic arrays, and indeed to achieve exceptional points in these structures. In our framework, the kind of crucial realization that allows us to get started and start saying things is that the analysis I presented at the beginning allows for complex valued material parameters, the imaginary parts of which we're using to represent, albeit in a slightly abstract way, the addition of gain and loss to the system. And then we can use this generalized capacitance matrix to once again look for coincident eigenvalues and eigenvectors. And there's one important point to highlight is that in our setting, we're actually looking for asymptotic exceptional points, what we're calling asymptotic exceptional points. So these are points at which this generalized capacitance matrix has an exceptional point. And that, of course, means that the full differential system has an exceptional point at leading order, so up to some error in delta, which we're able to quantify. And this, I should add, is it's not a weakness of the analytic approach, but as I understand it, represents the behavior of the system. The reason is that this radiation condition means that the symmetries that we're imposing on the resonators don't extend to the far field, and hence we don't get, at these exceptional points that we're searching for, we don't get exact degeneracy. Now, with this definition in mind, we're able to show that a system of two resonators, depicted on the left here, supports an asymptotic exceptional point of order 2, and indeed we can calculate the appropriate parameter values to make that happen. In order to kind of make clear the asymptotic nature of these exceptional points, we can simulate the full system numerically. So you see here the real and imaginary parts of the wavelength resonant frequencies, and you can see that there is an asymptotic exceptional point when the magnitude of the gain and loss is around here, somewhere around 5 times 10 to the minus 5. And further, you can, just by eye here, start to evaluate for yourselves that in this case, so here delta is something like 10 to the minus 4. The error is small enough that we're still getting the desired enhanced sensing response. And we have some numerics to support that. So we'd like to, in the last few moments, go a step further and look for higher order exceptional points for which we need to study larger systems. And so that the capacitance matrix is easier to work with in this case, we're going to make an additional assumption, which is that the resonators are relatively far apart, in which case we have the following result to describe the behavior of the capacitance coefficients. This allows us to see, among other things, the symmetry of the capacitance matrix, and it also nicely sets up efficient analyses of large systems of resonators in terms of this leading order approximation of the capacitance matrix. And with this result in hand, we're able to prove the following statement, giving the existence of a third order exceptional point in a PT symmetric system of 3 resonators. Once again, it's informative to look at the the corresponding numerical simulations. And here we're comparing on the left the resonant frequencies of the full system with, on the right, the eigenvalues of the capacitance matrix. And you can see that there's normalization going on here, but at tau equals 1 on the x-axis, you can see that the generalized capacitance matrix has this exact degeneracy, whereas this is only asymptotic in the full differential system. And we can take this method further and study larger systems still. So while a system of 3 resonators has only one third-order sub-wavelength asymptotic exceptional point, a system of 4 resonators has 4 of these points, so 4 different parameter values that give rise to such a degeneracy. Here in these plots A to D, we're showing the imaginary parts of the material parameters on at each of these exceptional points. And the thing that's nice to observe here is that each one has a different underlying symmetry. And this symmetry pattern continues to even larger systems. So if we take I think we take this one, A and D, and we continue these to larger systems, we see that even in much bigger systems of 8 and 14 resonators, we see there exist asymptotic exceptional points with the same symmetry. And indeed, for larger systems of resonators, the number of possible exceptional points grows actually very quickly, but nonetheless, this is nice because this demonstrates the value of this approach, which is that this potentially quite intricate sub-wavelength resonator system has been reduced to just a matrix eigenproblem, meaning that we can just attack it with conventional methods in order to reveal this behavior that would otherwise be quite challenging to understand in a precise and rigorous way, that is. I think that's a nice note for me to finish on. So I will briefly just share some references which have all the details that I've omitted. And then all that remains is to thank you for listening and stop there. Thanks.